Next, let's count maps between sets. Here is a notation that might be a bit weird. If A and B are two sets, then B to the A, like an exponent, shall mean the set of all maps from A to B. Why B to the A? Why are we putting the B first and the A last? It turns out that this has a good reason, namely the following theorem. Let A and B be two finite sets, then the size of the set B to the A is the size of B to the power of the size of A. So it's this is why this notation. It's similar to how this cross here imitates the multiplication of numbers. So let's restate this in simple words. In other words, the number of maps from A to B is the size of B to the size of A. Why? We label the elements of A by A1, A2, and so on, AN, so that the size of A is n. Now, any map f from A to B is uniquely determined by the n tuple f of A1, f of A2, and so on, f of AN of elements of B. The idea here is really simple. In order to encode a map from A to B, you just write down the list of all its values. So this will depend on a fixed numbering of the elements of A, so you know which element to put where in the list. But once you have fixed that numbering, you just can encode this map F as a list of its values. And this is bijective. So if you have the map F is uniquely determined by this list, and any possible n tuple of elements of B is the list of values of some map. So this gives us a bijection from the maps from A to B, or in other words, from B to the A, to B to the N, the set of all n tuples, that just sends a map F to this list of its values. Hence, the bijection principle yields that the size of B to the A is the size of B to the N, and this is, as we know from the power rule, the size of B to the N. But N is the size of A, so this is the size of B to the size of A, and we're done.